go from current slide. And we did, if my memory is right, example 6 before. We need to talk with one student if she comes in today. But so far, not here yet. Okay. We did finish chapter 1. I gave you the test. Is anyone here today that wasn't here Monday to get the test? Okay. Were there any questions that you've run into on the test? Everything fairly straightforward, clear, or clear as mud, or haven't looked at it yet? Or any questions? Again, I'll try to clarify anything the questions are asking, but it's not legitimate. Can you do this problem? Well, the answer is yes, I can, but I'm not going to. However, if you find anything in the book that's not exactly that question, I'll be glad to do that. Okay. So, if there's no questions there, we did get started on 2.1. I think we had started before, but we almost finished it. Did not quite finish. We did example 6. We're right ready for example 7. Is any question on that? And I think, yeah, going to have to work on this page because there's no white space on the others. So example 7. I think I talked about one like this, but I don't think we actually did it. Here's a function. Let me get my pen set up. Whoa, can't set it up there. Okay. If no questions, here's the function f of x is equal to x to the 1/3 power. Okay, time out. Remind me, what does it mean to have a rational exponent? What does that connote to you?
So it's like the cube, that'd be the cube root, right?
The cube root of x, exactly. The numerator is the exponent, the power, and that's 1. X is 1, that's no sweat there. The denominator is the index for your radical. So when you have a rational expression with a denominator, the denominator indicates you got a radical here, that will be the index of the radical. So you're absolutely right. That would be the same as x, the cube root of x. Okay. However, in doing differentiation, integration, and all that stuff, from now on, I'll always go to exponential notation, not radical notation. Okay? Radical notation, not easy to take derivatives and things like that. Always use exponential notation. Okay. The statement here is that this function, f of x, is continuous at x equals 0. And it's true. It's continuous everywhere. Okay? Cube roots, you can take negatives. Right? It's only even roots you can't take an even root of a negative number. But a cube root, a fifth root, a seventh root, a 17th root, you can take for positive numbers, negative numbers, any number. Okay? So it's continuous everywhere, including at x equals 0. Okay? Now, there is a graph in the book, and it's not on the slide set, so I can't show it to you. For those who don't have books, I'll hold this up for a few moments. There's a graph of this function, the cube root of x, x to the 1/3 power. Okay? Continuous everywhere, including at the origin. And of course, at the origin, the value is 0. Okay. Now, how would you go about differentiating this? The way we've been doing it so far. The limit as, help me out here, it's been a long time, at least 2 days. Oh, that long, huh? Okay. Limit as delta x approaches 0. Okay. You could do it as x approaches 0 too if you did it the second way. And in fact, that's the way the book is doing it, so let's do it that way. There are two ways you can approach this, and this is the x approaching 0. X approaching c way, okay? Of what then? Difference quotient. F of x minus f of 0 over x minus 0. Okay, nice. What is your f of x? And in this problem, I don't know if it really matters whether you use the exponential or the radical form when you're doing a limit. We'll use the exponential form they did in the book. That is x to the 1/3 minus, and what did we say f of 0 was? Not that hard. Say again? 0. Okay, so we won't even put anything there. Over x. I really should have my limit here as x approaches 0. Okay? Well, what is x to the 1/3 over x? I'll still keep the limit there. Dividing, same base, different exponents. Ring a bell? Is what? I saw the mouth moving, but I couldn't hear anything. Okay. Would it help if I wrote this x down here? What's the exponent of this x? Okay, if I wrote that as 3/3, would that be legal? That's 1, okay. Now, does that suggest anything? Say again? Yeah, that's the exponent of the denominators. X to the 1/3 divided by x to the 3/3. What would that leave you with?
Minus 2/3.
Where? In the denominator. Ah, okay. X 1 over x to the 2/3. Right? Now, let's take a limit of that as x approaches 0. What do you get? Okay, take the...
Indeterminate.
Well, actually not indeterminate. Undefined, because that numerator is never 0. It's always 1. So it's not just an indeterminate form. This is an undefined form, meaning cannot ever happen. The derivative of this function at x equals 0 does not exist. If it were indeterminate, it might. But this is a 1 over x to the 2/3. And when that approaches 0, it doesn't happen. All right. And here we have Cedric, right? Okay. I recall I have 3 Cedrics. Okay, you're one of the 3, so I'm remembering you now that way. And then Elise, I was thinking it was. Trying to find you. If you'll come check with me right before you leave. Okay. All right. We were just doing example 7 on page 106, and we just determined this as x approaches 0 does not exist. Now, they like to put equal infinity. Well, how do you know if it's a positive infinity or a negative infinity? You tell me that. You know, you can't. It's a vertical line. There is no solution to that. It does not exist. So that means the derivative does not exist at, that's a really ugly S, isn't it? That looks like an N. It must be morning, okay. I guess I got carried away. Okay, does not exist. Okay. Any questions on that? Okay. So f is not differentiable at x equals 0. Now, if you think back at the graph, and I'm not going to hold the book up again, but remember it did something like that. What was the slope there at 0? The vertical line. No slope, there is none. Anywhere to the left of that? Yep. And anywhere to the right of that? Yep, there is a slope, but not at x equals 0. It's continuous there. It's defined there. Everything's good there, except it doesn't have a derivative there because it is approaching a vertical line and is a vertical line there. All right, so that gets us through example 7. And this is the last little bit before we left. The only reason I even kept it on 2.1. Function that is not differentiable at a point at which its graph has a sharp turn or a vertical tangent line. The function is not differentiable at a point where it has a sharp turn. Remember your absolute value functions, not there. There are other functions that have cusp there, definitely not there, and where the tangent line goes vertical, like we just saw. So differentiability implies continuity. If it's differentiable, it's got to be continuous. However, it's not always differentiable just because it's continuous. It's a one-sided indicator here. Differentiable implies continuity. Continuity does not always imply differentiability. The relationships between continuity and differentiability summarized below. The function is differentiable at x equals c. It's got to be continuous at x equals c. No way it could be discontinuous or undefined there. Differentiability implies continuity. It is possible for a function to be continuous at x equals c and not differentiable there. So continuity does not imply differentiability. Quite often it will be, but most of it you can't guarantee it just because it's a continuous function. All right, any questions on that? And that does end the section formally. So let's do, and there is a proof in the book. And for those who are into proofs, please do them, but we need to keep moving a little bit more in class. So, homework exercises. Number 5 is at calcchat.com. 7 is also at calcchat.com. Any of the odds 9 through 13, they're all at CalcChat. 11's at CalcView. Any of the odds 15 to 27, they're all at CalcChat. 17's at CalcView. Any of the odds 29 to 35, they're all at CalcChat. 31's at CalcView. Any of the odds 37 to 41, they're all at CalcChat. 37's at CalcView. Any of the odds 43 to 47, they're all at CalcChat. And then there's an exploring concepts, and you can look at and explore 49 and 51 to your heart's content. They should be at CalcChat. If they're not, don't really stress over them too much, but they would be worthy of your thought. 53, again, CalcChat should be there. Either 55 or 57, both at CalcChat. 57's at CalcView. 59 should be at CalcChat. And 61 should be at CalcChat. 63 is graphical reasoning, so you can take a look at that if you'd like. And set 65, either one of those two. 67 should be at CalcChat. And then any of the odds 69 to 75, they're all at CalcChat. 69's at CalcView. Either 77 or 79, they're both at CalcChat. 77's at CalcView. Either 81 or 83 or both, they're both at CalcChat. 85 or 87, they're both at CalcChat. 87's at CalcView. 89's at CalcChat. And then you can look at 91 if you'd like. They claim that the B part will need graphing utility, so if you've got it, you can play with that. True false, 93 or 95, well worth thinking through that. You won't see many of those on a test or anything, but still worth your effort to think through it. And differentiable and continuity 97 should be at CalcChat as well. Any questions on 2.1? All right, let's move on to 2.2. All right, we're still in Chapter 2, differentiation. First half of most calculus. Okay, and we're now moving to 2.2, and I know y'all been dreading this. This is where we began sort of leaving our limits behind and just start using differentiation rules. Oh, boo hiss. They were so much fun, weren't they? Okay. Basic differentiation rules and rates of change, which we've been talking about all along. So we'll find differentiation rules using the constant rule. Okay? Find derivative of a function using the power rule. We'll find derivative of a function using the constant multiple rule, and we'll find derivatives of a function using the sum and difference rule. Oh man, all these rules, I think you'll find they're pretty simple and fairly easy to remember. But they like to name them and capitalize them even. That's really good. And then we'll continue with finding derivatives of the sine function and cosine function, and we'll use derivatives to find rates of change. That's where the rates of change come in. So let's talk about the constant rule. A real biggie. In this section, you'll be introduced to several differentiation rules that allow you to find derivatives without, oh shucks, the direct use of the limit definition. Okay. The constant rule. The derivative of a constant function. Picture a constant function. How would you picture a constant function for me?
2.
Say again?
2.
A little louder.
2.
2, okay. Alpha max equals 2. Okay, picture that for me. Tell me how you would graph it.
Just a horizontal line.
Horizontal line going through 2 and continuing through 2 forever and ever and ever. For every value of x, the y value is 2. That's it. Okay? What's the slope of that line?
0.
0. Okay, it has no slope. So guess what? The derivative of a constant function is 0. That is, if c is any real number, then the derivative with respect to x, now this is a number, not a variable, of a constant is 0. Okay, that's it. Horizontal line, slope is 0, derivative is 0, you got it. Notice that the constant rule, equivalent to saying the slope of the horizontal line is 0, demonstrates the relationship between slope and derivative. Pretty clear, right? Should we harp on it a bit longer? Okay, probably not. Okay, let's see if they have example 1 here. Oh, these are hard. Okay, what's the derivative of, if y is equal to 7, what's this derivative?
0.
0. Oh, good. Y'all are quick on the draw here. Okay, how about f of x equals 0? How about that one?
0.
L prime is 0. Ooh, wow. Okay. I must be teaching really well. How about st is negative number, negative 3?
0.
It's still 0, yeah. It's derivative of a constant is 0. How about if it's k, pi squared, where k is a constant?
0.
No.
Why not? Pi is a number. 3.1415. Just a number. K is a constant. Derivative of that is 0. Derivative of any constant. 4,845 thirds is a constant. Okay? Derivative of that is 0. Make sense? Oh, shucks, we're already on to the power rule? Wow, y'all are quick. Okay, so let's look at the power rule. Now, before proving the next rule, it's important to review a procedure for expanding a binomial. Okay? Now, we did Pascal's triangle, I think, didn't we? Okay, I thought we had. This uses it, but it doesn't show it. I'll tell you another way of expanding a binomial. Okay? If you're doing x plus delta x squared, take the first term to this power, x squared, and this term to the 0 power, so it's 1. Okay? Now, then what you do next is multiply this exponent times the coefficient, okay, and divide then by the number of terms, second term, so divide by, no, the first thing, so it's 2 times this to the first power times this to the second power. Okay? Now, this time, the exponent here times 2 divide, okay, this was the first term. Second term, divide by 2, and that gives you a coefficient of 1, but you drop this by 1 and raise that by 1, so you got x squared. So your first term goes down in powers, your second term goes up in powers, your coefficients you can think of as that little rule I just gave you. Let's try this one. X plus delta x cubed. X cubed times delta x to the 0th power, coefficient 1. Okay? Well, the coefficient here was 1. Then 3 times 1 is 3, divided by 1, because it's the first term. That gives you a coefficient of 3. drop this one by 1, x squared, increase that by 1, delta x. So there's your second term. Okay, 3 times 2 is 6, divided by second term, and that makes it 3. 6 divided by 2 is 3. So 3 is your coefficient again. Drop this one by 1, increase that one by 1. There's your third term. Okay, coefficient of this first one is 1 times 3. 3 divided by 3, third term, 1. This one drops by 1, it disappears. This one goes up by 1. Boy, that's sort of awkward. Don't you like Pascal's triangle better now? Okay, I do. And it keeps on going. You can do it, x to the 4th, and then 4 times it, so 4x cubed delta x. Next would be 12 divided by 2 is 6, x squared delta x squared. 12 divided by 3 is 4x delta x cubed. And 4 divided by 4 is 1. And it just keeps on trucking. Okay? You can see Pascal's triangle here. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and 1, 5, 10, 10, 10, 5, and 1. Okay. The awkward drawing for Pascal's triangle. So much easier with Pascal's triangle. And it keeps going. You can do them ad infinitum. Okay. The general binomial expansion for a positive integer is, and there, they cut it short, but it's certainly there. X to the n plus n times x to the n minus 1 times delta x. So you're dropping the x by 1 power and raising the delta x by 1. And then the next one is, here's how they do it. Yeah, well, the same thing. N times n minus 1. I usually do it this way, but it doesn't matter. N times n minus 1 divided by 2, because that's the second term here. And it's x to the n minus 2, delta x to the squared, because you're raising that by 1. Now, you might say to yourself, is there any reason they put this up here but this one down there? Not really, but they wanted to emphasize that the delta x squared is going to be on all those terms. Only a delta x here, but all those will have a delta x squared. They'll have higher powers of delta x after this one. This one goes up to n, but they all have a factor of delta x squared in each of the terms. Now, why didn't they include this and say delta x in each of the terms? Well, must be a reason for that. So that binomial expansion is used when proving a special case of the power rule. And we were certainly wanting to prove that, right? We don't want to just know what it is, we want to know why it is, don't we? Okay. So if n is a rational number, not integer, rational number, 1/3, 3/5, 17/14, whatever rational number, okay? F of x equal x to the n. N is not just an integer, now a rational number that is differentiable. Always differentiable. And, I really mean always. It is, but we'll get back to that later. Not by this rule, though. We'll get that in that. And derivative of x with respect to x to the n is n times x to the n minus 1. Okay? And for f to be differentiable, x equals 0, n must be a number such that x to the n minus 1 is defined on an interval containing 0. We just saw when that was 1/3, it doesn't work. Okay? So those are the cases. So they did put in the weasel words here. N must be a number such that x to the n minus 1 is defined. In other words, if that comes up being 0 in a denominator, you can't do it. Okay? So they did give themselves an out here. And it works. Okay. So there's the power rule. Okay. Now, they're going to use that thing that we're talking about in the proof of it, and I bet you in the book they do use that proof, and you certainly are welcome to go through that to your heart's content. But the point being that it's not a hard proof, it's just messy to do because you've got a lot of writing to do, and they take up long lines here, and you have to allow a lot of dots in them. But basically what happens, remember this being the case here, all these have delta x squared in them. And remember, our limit is going to let delta x go to 0, and you can divide out one delta x, manage a way to get rid of one, but you don't get rid of the rest of them, all those become zeros. That's the arm waving proof, okay? Wave your arms and see if you can get it to work. Okay. So, and here's what I was worried about. This proves the case for which n is a positive integer greater than 1. So even though this says any rational number, the proof works for any n greater than 1. Okay. All right. Okay. So, when using this power rule, then, the case for which n is equal to 1 is best thought of as a separate differentiation. Okay? There's really nothing wrong with n equal 1, but let's do it. Okay? Let's go back and review the power rule again. The derivative of this is n times x to the n minus 1. Okay? So what if n were really 1? This one, n is 1. So this would be a 1 times x. And what's 1 minus 1? 0. Okay? So that would give you a derivative of just n. Okay? No. Okay, yeah. And n is equal to 1. So that would give you the derivative of 1. So they say, here's the power rule. Well, guess what? The power rule is written on the previous page, gives you that. There was nothing special or anything about it. Now, this rule is consistent with the fact, what is this function? Y is equal to x. What do we know? We have a special name for that function. Y is equal to x. Huh? Identity function, exactly. Okay, and what can you tell me about that identity function? You can tell me two things right off the top. Three, maybe. I didn't see you come in. Sorry. Snuck in on me here. Okay. Gotta find you, though. Ayana. Right, no. Taylor, sorry. Okay, I was so wanting to get her name right, but you're not her. Okay, sorry. So what are two things you can tell me about that function? Maybe three or four. Tell me something you can tell me about that function. Y is equal to x. Second? Wow. One more time. Okay, yeah. The x and y's are the same thing. That's why it's called the identity function, because x is equal to y. Y is equal to x. Perfect. What kind of function is it? If you were to graph it.
It's a line.
It's a straight line, of course. It's a linear function. What can you tell me about that line? The slope is 1. Oh, wait, what is slope? The first derivative. Look at that. So, derivative of x, the slope of a identity function is 1. Because the slope is 1. This one happens also to have a y-intercept of 0. Okay, it goes to the origin. Okay, so that doesn't matter to the derivative any, but it just happens to go through the origin. All right, very good. Any questions on that? So the derivative of x d by dx, oh, I like saying d by dx. Okay, d by dx of x is just 1. Now, please, if you're a pure mathematician, close your head and don't think about this. If you wrote it this way, okay, if you wrote it dx dx, just didn't put the x there, but did like, what does that look like that would be? Oh boy, that looks like that would be 1 too. Now that's not what it means, because this is an operator. D by dx is the operator operating on x, and that's equal to 1. And just forget the fact that looks like that would be 1. No, it is. It's exactly 1. Okay, good. Any questions? Okay. So let's do some of these. What's the derivative of f of x? Don't read my sleep. Okay. 3x squared. 3 times x, and then drop the derivative of the exponent by 1. 3x squared. Perfect. Perfect. Y'all look good. Close your eyes. Okay. Got it. What's the derivative of that? Oh, whoa. Messy. Radical form. Hate those. So what would you do?
You can make it x to the 1/3.
X to the 1/3. Write it in exponential form. And then what would be the derivative of g then? Negative what? Negative 2/3. Excellent. Okay. You rewrite this as x to the 1/3, and then d by dx of that. Ooh, that's good. That would be 1/3 x to the 1/3 minus 3/3. We did this, didn't we? Negative 2/3, and that would be 1/3, because 3 is in the denominator. This moves that to the denominator. X to the 2/3. Okay. Is that defined at 0? No. Not even indeterminate. It's not defined at 0. That was the one we just did. Everywhere else is defined. 0.0003, that would be defined. You have a really small number, really huge number, but it would be defined. And negative 0.000001 still would be defined, but not at x equals 0. Good deal. Any questions on that? Power rule says, write it in exponential form, the exponent times the coefficient. We haven't gotten there yet. I'm saying it. Ignore that. The exponent times 1, we'll just say it that way, and then x to the n to minus 1. That makes it minus 2/3. And if you don't like negative exponents, put it downstairs and lose the exponent. Y'all remember that, right? Okay, good deal. See if we got another one. How about that? Can you do that? I don't like exponents in the denominator either. So what would I won't like variables in the denominator.
X to the negative 2.
Right, that is d by dx. They left that out. Yeah, there it is. X to the minus 2. Okay? Because 1/x squared is x to the minus 2. Now you've got it. Remember, all it takes is a rational number. It doesn't have to be a positive number or even an integer. It could be a rational number. So what would be its derivative?
Negative 2 over x to the 3rd.
Okay, negative 2x to the minus 3, which is the same as negative 2 over x to the 3rd. Now notice this. This isn't moved downstairs. 1/3, the 3 was downstairs because it was already downstairs. Negative 2 stays upstairs. Okay? But x to the minus 3 moves downstairs and becomes x cubed. Right? Make sense? All remember from before. Okay, is there a d? No, there's no d. Okay, in that example 2c, note that before differentiating, get the variables out of the denominator, get the variables out from under radicals, and write them as exponents. If at all possible, write them as exponents. So rewriting the first step in rewriting is the first step in many differentiation problems. First, write it like this. Take it out of the denominator, make it x to the minus 2, then it's easy to differentiate. Minus 2 times 1, minus 2 times x to the subtract 1, minus 3. Then you can move it back downstairs if you want to. Okay. And usually, not always, but usually, if they give you the problem like this, then they sort of expect the answer to be back in that same type of form. So that earlier one, if it gave the problem as a radical, you took it out of the radical and dealt with it, but then for your answer, put it back as a radical. That's just sort of a general rule. It's not required. If you got the right answer, it's the right answer. Okay. If you were doing WebAssign, though, they're looking for one answer, and a lot of the problem is trying to guess which answer they're looking for. Okay. That's why I don't really care that much for WebAssign. While I'm on that subject, I finally heard back from Cengage, and they said, here are your courses you requested. I requested setups for 7 courses, and they sent 4. This one not being included. Sorry about that. And one of the 4 they sent back was the wrong course. Okay. They said it was 113, but they sent me back Math 100, even though everything had been... I'm not too impressed with Cengage. They have a good package in the Cengage Unlimited, but the company is, well, no, we won't go into that. All right. Any questions on this? Okay. Let's see. That was example 2. Before we get to constant multiple rule, though, we've got examples 3 and 4 to do. So let's see about doing those. Okay. Go. Why is it not writing? Okay, there we go. And by the way, example 3 and 4 can be found at larsoncalculus.com for interactive versions of these types of examples. So it says, find the slope of the graph of f of x is equal to x to the 4th for each value of x. And they give you 3 of them. X equals -1, x equals 0, and x equals 1. Okay. How do you find the slope of a graph? On your first test, you probably had to fiddle around and take points close by and estimate. Oh, that's right. Very good. Now, I hope none of you take offense at this. I'm not making fun of it. It's just something I've noticed. And I hope you're not bothered by it at all. But at our church, especially at the main service, they usually have a children's service. Okay? Get all the kids to come to the front. And then the pastor or youth leader, somebody up there, gets them in the front and tries to get them all settled down. And then usually starts with a question, a pretty simple little question. And all the kids are there just, I'm not supposed to talk in church, So, and finally one kid will think, nobody's talking, so he'll answer, Jesus. Now, in church, it's usually a good answer, right? Okay. It's Christian church anyway. So, when you get to Cal 1, the Jesus answer is usually take a derivative, okay? So that's what we do. What is the slope? Take a derivative, okay? So that's going to work most of the time for you, just like it does in church for kids. But not, okay. Sorry, let's not go there. All right, so you said take a derivative. Let's take a derivative. F prime of x, that's one way to express it, is 4x to the 3rd. All right, very good. Everybody see that? Okay. Now, if you want the slope at x equals -1, guess what you do? F prime at -1, and what would that be?
-4.
-4. Perfect. F prime at 0. This is my favorite. 0. And F prime at 1. 4. That would be the slope at those 3 places, okay? Now, if we could picture this, what does this kind of look like? Anyone remember what x to the 4th looks like? Graph of that? It looks a lot like a parabola. It's a little bit fatter than most parabolas and flatter at the end. Yeah, fatter and not really. Well, but anyway, flatter at the bottom. So it's coming down pretty steep here, and at -1, I can easily see the slope being a -4, but at 0, guess what that slope is? 0, and then going up again, it goes up really steeply there, so I can easily imagine at 1, you'd have a slope of around 4. So yeah, that at least makes you feel warm and fuzzy. It's in the right ballpark, and that is exactly right. Make sense? Slopes at these 3 points. All right, make sure they got them right in the book. Oh, look at that, they did. Good for them. All right, any questions? All right, let's do example 4, I believe it is. Okay. Again, this one's at larsoncalculus.com. And by the way, in the book, I was waving arms and I didn't notice that there's your flattened parabola. Okay? Not exactly a parabola, flattened here. Really steep slope there, -4. 0 slope at 0, 0. And a really steep slope there. But a positive slope. This one's negative, this one's positive, +4 there. Well, I got through talking because that was all hard. Okay. Example 4. Find an equation of the tangent line to the graph of f of x equal x squared when x is equal to -2. So we want to find equation of the tangent line. Okay, of f of x squared, f of x equal x squared. This is a parabola, by the way, when x is equal to -2, right? How would you begin? Ah, yes, take a derivative. Good choice. So f prime of x is going to be 2x. Okay? What does that tell you?
You plug in that x value and you get a y value.
Okay, where are you talking?
You plug in -2, that'll give you the
Yeah, but where do you plug it in?
into the x.
Which x? Into the derivative. Okay, good. Okay, is that what you were saying too? Okay, right. Okay, because I'll explain my reticence in a minute. Okay, and what will this be? 2 times -2, and that will be. They seem to like -4 for slope, don't they? Okay. All right, that gives you the slope. That doesn't give you the equation of a tangent line, though. What do you need to have an equation of a line? Say again?
Y is mx plus b.
Exactly, okay? Y is equal to mx plus b. That's going to be the equation of a line. What does the m stand for? Slope. Hey, we got it. So that gives you part of what you need, but it doesn't give you all of what you need. But we can plug that in. Y is equal to -4 because the derivative tells you the slope at that point. -4x plus b. But that isn't fully an equation of a tangent line until you know what b is. Now, how can we figure out what b is? Say again? Okay, yeah. Now that may be a little hard. If you knew y-intercept, we'd know b. I don't know what the y-intercept is.
Point slope form.
Ah, okay. Rather than mx plus b, which will work, and we'll come back and do it with that one, we could have used this one. How does that go, anyway?
Y minus y1
Okay.
equal to
M times x minus x1. Okay, that would be all right, nice and groovy if you were back in the 60s. And we got our slope, -4. But we still don't know, that before we didn't know what b is, now we don't know what x1, y1 is, do we? Okay, which original equation you talked about?
X cubed.
Ha! Yes, x squared, right? Yeah. Go back to this and do what? Ah, that's why I was wondering before, I didn't know which way Dawson was going, whether you were plugging in here or plugging in there, because I didn't know if you were looking for the point or for the other. So yeah, if you plug in, what do you plug in there?
Y minus.
Okay, we'll plug it in first. F of negative 2 is equal to negative 2 squared, which is 4. So, what does that tell us? This is your x1, this is your y1. Now we can use Dawson's form, which is y minus 4 is equal to minus 4. They like 4s, don't they? X minus a negative 2. Okay. So clean that up a little bit. It'd be y minus 4 is equal to minus 4 times what?
Plus 2.
Plus 2. Okay. You don't have to take all these steps if you don't want to. What do you do now? Y minus 4 is equal to help me? Negative 4x minus 8. And now what do we do? Add 4 to both sides. That sounds like a capital idea. And that gives you y is equal to, because that goes to 0, minus 4x minus 4. I told you they like minus 4s a lot. Okay? There we have it in slope-intercept form. Now we know the y-intercept for that line will be a negative 4. Okay. Now, if you like point-slope formula, that's it. Because you see, plugging in your value x equal 2 gives you the slope on your derivative, but it gives you a point on that line for your other. And that's the point that this derivative is valid. So that gives you your point, that gives you your slope, point-slope formula, perfect choice. But could we do that with Bill's form, the slope-intercept form? We don't know the intercept. But we still know an xy value, don't we? We know that an x is negative 2, y is equal to 4. So let's plug that in here. 4 is equal to minus 4 times negative 2 plus b. And what does this give us? 4 is equal to, second, 8 plus b, and then subtract 8 from both sides. Ooh. Okay. And what does that give you? B is equal to negative 4. Yeah, and then we just plug it back in here. Y is equal to minus 4x minus 4. Same answer both ways we did it. And so it doesn't matter which way you do it. Either one works. You still got to figure out the point, but you get that by the x equals negative 2, plug it into the f, you get the point, plug it into f prime, you get the slope. Got it? Make sense? And there you have your equation of y. Equation of y is always going to look like that. You don't have to write it in slope-intercept form, but that's the handiest, most convenient way to write it. So I like that. You could have left it like this if you wanted to, but please don't want to. Okay? Clean it up a little bit. Okay? But usually when you clean it up, the simplest form is that. Okay? Any questions? All right, that was sort of all over the page, wasn't it? Oh, and they got it right in the book. Good for them. Sorry, I can't pound on my desk. Okay. So now I think we're now ready for the constant multiple rule. Okay? Now the theorem here. If f is a differentiable function, which we're always going to assume it is, and c is any real number, positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Even 0, that'll be work too. 0 is not very interesting though. Then c times f, say it's 2 or 0, that would be 0, is also differentiable, and here's what the derivative is. E to the x, I love saying that, of c f of x, what you can do, that's the constant, just pull it on the outside of that operator, c times, and then they change their operator. You don't have to. You could have said c by df dx. They would change it to f prime. They love to go back and forth with the different notations for derivatives. Whatever notation you use, that's it. So just pull the t on the outside and then take just the derivative of your f of x. Okay? Pretty straightforward, right? And I'm pretty sure they do a little proof on it, and they do it using the limit. And I know you didn't want to leave limits, so if you're missing them that badly, do the proof. It's pretty straightforward. Okay. Now, they do a few more statements here, and I like this one. What if this had been d by dx of f of x over c? Now, everything I said before would be true except one little thing. C, it says, is a real number. Yeah, except
0.
Yeah, it can't be 0. Okay, so with that exception, c not being equal to 0, what's that derivative?
F prime of x divided by c.
F prime of x divided by c, yeah. Or 1 over c times f prime of x. Yeah, exactly. Just pull out the constant. Here the constant is 1 over c. As long as c is not 0, that's just a constant, just like c was a constant. So it doesn't really matter, but they did make a point of saying that. Okay? So now we move to example 5. No, look. Okay. If that's your function, what's the derivative?
15x squared.
Oh boy, you cheated, didn't you? Okay, you combine two steps at once. Okay? Pull out the 5 and then do derivative of x cubed, which is 3x squared. 5 times 3 is 15. So sure enough, 15x squared. And is it okay if I show you the shortcut? Okay, just like we did before. Take the exponent, multiply it by the coefficient, drop the value below 1. Okay. That's what you did, wasn't it? Okay. Any questions? You can split it up like this if you want to and use every rule in the book, or just cut to the chase. Exponent times coefficient, reduce the power by 1. Much easier that way. But maybe less fun. Okay. So let's do this. Oh, what would that be? What's the first thing you're going to do?
Make the exponent. Take the numerator, denominator, put it in.
Yes, exactly. Yeah, I don't like variables in the denominator. Numbers down there are fine, as long as they're not 0. Variables, I don't like down there. Okay, so take it and move it to the numerator. So what would that be? Second, 2 to the negative x. Perfect. 2 to the 2 times x to the minus 1. Okay, 2 times x to the minus 1. Okay, move it upstairs and negate the sign. So how do you do that derivative? Perfect. Negative 2, x to the minus 2, and then since they started off putting them in the denominator, put them back down there and move that back downstairs. So it's negative 2 over x squared. Perfect. Everybody see that? Okay? Pretty straightforward. Boy, isn't differentiation easy so far. Okay? How about this one? What would you do there?
Make it 4t squared times 5 to the negative 1.
Okay. Said I didn't mind numbers in the denominator. It's just the variables. Variable not in the denominator. Leave that as 4/5. There's your coefficient. Okay? And then do what with it? Second? Yeah, times 2. That would be 4/5 times 2 is?
What you're trying to do is
8/5 times t
minus
1, which is just t. So 8/5 t. Okay. Now, if you need to take the time to do it, please take the time. If you like to do it better by showing more steps, please show more steps. Do the way that makes the most sense to you. Okay? So first thing I would do is pull all the constants outside and make it 4/5 times this. Now they then say, well, that's a constant multiplier, so pull that outside, then take the derivative of that. The derivative of that is t So it'd be derivative of this is 2t, and 2t times 4/5, that would be 8/5 times 2. Okay. So however you like to do it, okay, whatever you see best, okay, go for it. Does that make sense? Does everybody see what all the steps we're doing there? To me, writing too many steps almost good. It increases my opportunities to make a stupid error. You know, so if I can do it in one step, at least I've decreased all the different steps in there where I could have made some dumb mistake. But y'all don't make dumb mistakes, do you? Good. Okay. All right. How about D here? Whoa! What do you do with that? All right. Write that as 2 times x to the 1/2, and what would be that derivative? X to the minus 1/2, which is 1 over square root of x. There it is. Okay, x to the minus 1/2 is a perfectly good answer. However, I bet you in the back of the book and probably on WebAssign and places like this, they'll change it back to have it in the same form they had to begin with. But who knows? Sometimes backs of the book, the typesetters are real lazy, and this is easier to set than that, so they'll leave it in that form. So it's hard to say. They're all right answers. Nevertheless, what WebAssign tells you it may be wrong is not. They're right. And both of those are correct answers. And you notice the 1/2 exponent times 2 is 1. So that's what happens to your 2 there. Does that make sense? All right. So that's using constant. Oh, there's more. Yay. Okay. What about that one? Oh, man. It'll be your first step. Okay. All right. So what would that give you? X to the 2/3. But it's still in a denominator. All right? Okay. Your exponent is your numerator and the index is the denominator. So that would be x to the 2/3. You see that or not? Okay. But it's still in the denominator. So what else could you do to it?
Just make it 2 times x to the negative 2 over 3.
Okay. Not 2 times. The 1/2 is your numerator, is your coefficient here. 1/2 times x to the minus 2/3. Right. Okay. Everybody agree with that so far? Ah, there it is. Now what do you do with that? Okay. And what is minus 2/6? Minus 1/3. That's the first part. Unfortunately, the easy part. Times x to the minus 5 over 3. Excellent. Okay. And now if you want to put it back downstairs again, what would that be?
Negative 1 over 3.
Negative 1 over 3 times to the 5 over 3. That's certainly fine, but they didn't put it back in that form, did they? So if you did take it all the way back to that form, what would that be? Still the cube root, but this time of x to the 5th. They didn't do it. I'm all in favor of not doing it. In fact, I'm really happy with it once you did the negative 1/3, leaving it just like that. But you could move it downstairs if you wanted to. Okay. So another answer for this would be negative 1 over 3 times the cube root of x to the 5th. Now, I did want to point this out to you, too. When they first did this, and I failed to point it out to you, but we'll use this one. You could also write that radical expression as the cube root of x to the 5th. That's right. Both of those are the same. The cube root of x raised to the 5th is the same as the cube root of x raised to the 5th. So you can either take the cube root first and then raise it to the 5th, or raise that to the 5th power, and then take the cube root off. Most of the time when your numbers are nice, like this does have a cube root, take the cube root first, then raise it to the 5th. Otherwise, this could be a huge number, and then finding its cube root. Calculators will still do it easily, but if you're doing it in your head, much better to do that. I like that better. If X has a cube root, do that first, then raise that to the 5th. Keeps the number smaller, and I'm lazy. Okay, so that's E. Okay, we even have an F here. Don't make them, but we can do them. Oh, wait, maybe. Oh, yeah, there it is. All right, how about that? Oh, goodness, it got harder and harder, didn't it? What's that one? Okay. Anyone do that? I was kidding the folks. Negative 3 halves. That's not the easiest one up there, just about, isn't it? It's just negative 3 halves is your coefficient. X is your variable. The derivative of X is 1. Negative 3 halves. Perfect. Okay. Exponent times coefficient. 1 times negative 3 halves. Drop that by 1. X is 0 is 1. Negative 3 halves. Okay. They were getting harder all the time, but then they eased up on you big time. All right. So I think they express the constant multiple rule. Oh, yeah. Now they're going to show you what we've been doing. Okay. Constant multiple rule and power rule can be combined into one rule. That combination rule is d by dx, I'll say that, of c x to the n is simply take the exponent, multiply it by the coefficient. They do coefficient times x, so it doesn't matter. We already do. And then drop the exponent by 1. Okay. That's what we've been doing. Right? So, welcome to do separate if you want to, but that's the easy way to go. Make sense? So I didn't cheat you too much. I just one slide ahead. All right. That's constant multiple rule. And they are skipping example 6. It must be hard, huh? Okay. Let's see. All right. Let me erase all this. No, I think I did bring my watch today, so y'all will keep me from going over, won't you? Y'all are kind. Okay. Very kind. Okay. Example 6. Y is equal to 5 over 2x cubed. It's helpful to be able to read. 5 over 2x cubed. What would you do first? Second? Help me out. Anybody? Make a guess. Okay, what moved to the top? Okay, no, okay. Coefficients stay pretty much where they are. Numbers stay where they are, unless they're exponents. So it'll be 5 halves. That's your coefficient, 5 halves. Separate it, okay, times what? Now move x to the negative 3. Perfect. That's my first step, too, okay? And where do you go from there? That's your y. What's your y prime? Perfect, perfect. And that is a perfectly good answer. However, I'm just guessing they'll want to rewrite it as minus, numerator is the 15 part, denominator is 2x to the 4th. Now that's just a guess. I don't know for sure if they're going to want to rewrite it, but that's what my guess would be. Both of those are perfectly correct answers. I hope anyway. Let's see if they are. Negative 15 over 2x to the fourth. Yeah. Got it. Make sense? All right, good deal. Let's do the B one then. Y is equal to 5. They like 5 now, don't they? Over 2x cubed. What? What would you do with that? I heard competing.
Denominate first.
Second?
Cube denominate first.
Yes. Please excuse my dear Aunt Sally. I don't know what she did, but please excuse. Yeah, let's do the exponent first. 5 over 8x cubed. And then I would do one more step to rewrite it as what? 5/8. That's your coefficient. A little louder. X to the minus 3. Ha! I'm ready to roll on that one. Okay? I like getting the variable in exponential notation, not in denominators, not in radicals, exponential notation. So what's your y prime now? Negative 15. They like that. 2 8s. X to the minus 4. And just judging from what they did last time, I would guess they want it as minus 15. So the only thing left in the numerator, and the denominator is 8x to the fourth. All right. Let's see if they got that right. Good for them, they did. All right. Any questions? Make sense? Okay. Let's do number C. Letter C. Y is equal to, well, they finally gotten away from 5s, 7 over 3x to the minus 2. Okay, not a whole lot of difference here, is there? Oh, yes, there is. What would this be? Let's rewrite that. 7/3, there's your coefficient. X what? X squared. Move it upstairs and lose the sign. Okay, change the sign. So we're ready to roll on this. What's y prime? Say that again. 14/3 x. That is just about as simple as you can do it. Let's hope they didn't botch that in. No, they didn't. They left it just like that. Is this making sense?
So you can still have a negative sign for the exponent even when A is already in the denominator?
Because when you moved it upstairs, you changed the sign. So yeah, you lost the negative sign. Now you see here it was downstairs. When you move it upstairs, you have to change the sign and you make it negative. That's what introduces the negative sign. Once you move this one upstairs, change its sign, it becomes positive. No, you aren't on the minus sign anymore. Yeah. Okay. Don't make extra work for yourself. That's my job. Okay. Now, D, Y is equal to 7. They get stuck on these numbers, don't they? Same type principle here. 3x to the 3x to the minus 2. They're just getting tricky on it, is all they're doing, isn't it? What would that be? Okay. You have to tell me where to put it. No, it's not a -9. I'll tell you that. Okay. Okay, I think you're going in a good direction. 7 times what? 3x in parentheses squared. Yes, let's take that whole thing to the -2, move it upstairs and make it a positive 2. Okay, now move from there. What does that give you? 7 times what? 9x squared. Okay, So what does that give you? 63x squared. Now we got it in a form I like to see, so let's do our y prime, and what would that be? 126x. Nice round number, yes, one of my favorites, okay? Let's see. Oh, yes, they got it right. Good for them. Does that make sense? Okay. Please. I did tell you what it takes to be a good mathematician, right? Be a little lazy, yes, of course. So don't make any extra work for yourself. Find the easiest way to do it, you know. Find the simplest way. Get that thing upstairs so you lose that minus thing, and then proceed from there. There are other ways, which I don't want to even go into, but you could do it other ways. That's the easy way. All right. Any questions on that? All right. Okay. We go to, I teach so many different courses, it's hard to remember. We go to 1140, don't we? Yeah. Okay, good. All right. So, we've used the constant multiple rule almost to death. So let's go to sum and difference rule. Oh boy, these must be hard if they saved them to the end. Sum and difference rule. The sum or the difference of two differentiable functions, so given that f and g must both be differentiable, is itself a differentiable function. Okay? Moreover, the derivative of f plus g or f minus g is either the sum or the difference of their derivatives. Oh man, didn't see that coming, did you? Okay. So d by dx of f plus g, that's a new function, sum function, just the derivative of sum is the sum of the derivatives. That's it. Or the derivative of the difference is the difference of the derivatives. Same thing. Hopefully, what you were wishing for, you know, what you were hoping it would be that simple, it is. Okay? Sum and difference rule, just hopefully like you were expecting. Okay? And they do get a little proof here using, I think they do, yeah, using your limits. And if you're missing them that badly, please do the proof. Okay. Let's move on to example 7 if they do it. Yes. So let's do that. All right. Now here's the function f. I don't see a g here. Well, let's think. F is a sum of this plus this. But since there's your f, g, and h, or it can't be f, g, h, and k. Okay. So yeah, that's the sum of three functions, or actually the difference and the sum. So how do we take its derivative? F prime. 3x squared, perfect. Minus 4, and that's all she wrote because the derivative of a constant is 0. Exactly. Okay, so that 5 is out of the picture now. 3x squared minus 4. Wow. I wish I could make it harder. I've tried, but I can't figure out any way to do it. Okay. How about this one? What would be your g prime? I'll even show you that part. What would be that? Negative. I heard that. That's good.
Negative 2x to the third.
Great.
Plus 9x squared.
Great.
Minus 2.
Minus 2. Excellent. Way to go. See how simple this is? Okay. One step. How do you eat that 5,000-pound elephant? One bite at a time. Okay. So don't let anything overwhelm you. Just do the stuff that you see as you see it. Does everyone see how he got that? He spouted it out, but does everybody see how it happened? You could have done it on your own if he hadn't said it so fast, right? Okay, good deal. Let's do the C point. Uh-oh. What do you do there? Help me. Second? Okay.
Well, you can apply his own.
Let's rewrite it, yeah. How would you rewrite that before you even try to take a derivative?
Could you...
You got 3x. Just 3x over.
Okay, 3x. Yeah, 3x. Yeah.
Plus
So-
1 over x.
Yes, you put this x over each term and go from there. So it's 3x. What's the next one?
Plus 1 minus
Minus 1. Perfect. Oops.
plus 1 over x.
Plus 1 over x. Am I still liking this? Do I like it yet? I like the first two. I don't like the third. What do I do with it?
Just going to go back.
Right, it's-
Differentiate that. The sign is going to change, but you're going to put it up in the numerator.
Okay. I think you're saying the right thing. My hearing's so bad though. I would write that as 3x minus 1 plus.
That'd be 0.
Second.
I was going to do differentiation 1 over x.
Okay, I don't want to do 1 over x. I don't like
But
doing
you're
x.
going to do x, you're going to make it x to the minus 1.
X to the minus 1. That's why I thought you had said, but I couldn't hear well enough. Rewrite this as x to the minus 1. Now let's take a derivative. And what would that be? First one's really hard. 3, okay.
3 plus
Second one's even harder.
0.
0, yeah, okay. That was really hard.
Negative 1 over x squared.
Negative 1 over x squared. So 3 minus 1 over x squared. Now, I think they skipped way too many steps, especially to begin with, but y'all didn't seem to mind. I would have written this as 3x minus 1 plus x to the minus 1, just like Bill said, okay? Then take a derivative of this, that would be 3, 0 for that one, minus x to the minus 2, and that would then be 3 minus 1 over x squared. And to me, that's a perfectly fine answer. For some reason, I guess because their original problem was a quotient, they want this as a quotient, so you can multiply, you can put this over x squared as well, but if you do that, you have to multiply that by x squared, because x squared over x squared is 1. Okay, got it. So this is 3x squared minus 1 over x squared. Nothing magical about that answer. I think this one's just as good. In fact, I like it better. It's fewer keystrokes, and I'm lazy. Okay, so it's just as good. Okay. But both of those are legitimate answers. So if you're ever taking these standardized tests and you don't see the answer in the form you want, try monkeying around with it and see if you can get one of the other forms. Of course, y'all know that. Y'all are experts at least, right? Okay, so that was C. I think I'm going to need to erase what I've got here. Can y'all live with me erasing it yet? You okay with it? All right. Now you still need me to leave it there a little longer? Okay. Okay, this one? Getting from here to here. Okay, derivative of 3x is 3. You got that one? Derivative of minus 1 is 0, so we don't need to write that down. Okay. Derivative of this will be minus 1 times 1 is a minus 1. Drop this by 2, drop this by 1, make it negative 2. Right. Then they wrote the 3, forget about this part here. Write the 3 minus, and x to the minus 2 is 1 over x squared. Right? Okay, so that's how we did that. And then to get their final answer there, see, they got that too. And to get from here to here, you multiply this by common denominator, x squared, so you multiply the numerator and the denominator by x squared. So you get 3x squared minus 1 over x squared. 3x squared over x squared minus 1 over x squared is 3x squared minus 1 over the common denominator x squared. That's just extra math, extra. I guess.
So we can't leave it like 3.
Huh? This answer is perfectly good to leave it just like that. Perfectly good to leave it just like that. That's the correct answer. Okay? There's nothing you have to do beyond that. I guess I should have written y prime equal that, because y is equal to that. Okay. Make sense? Anyone else have a question before we move on? Okay. So let me erase this if that's okay. Everybody got it? And let's do the D part. Oh, I thought there was a D part. Nope. Sorry. I was looking forward to D. Okay. So now we do derivatives of sine and cosine functions. Guess what, team? I think our luck has run out. Believe we will need to do well, we don't have to. They tell us what it is. Derivative of a sine function and derivative of a cosine function, they just tell us what they are. Derivative of sine is cosine. Derivative of cosine is minus sine. That little minus sign, not the S-I-N, that minus S-I-G-N, is going to be what throws you for now forever, okay? Just remember, derivative of cosine is minus sine. Now, it's almost worth doing the proof. We just don't really have lots of time. Let me give you a graphical explanation of this. So let's do a sine graph and a cosine graph, okay? I hope y'all remember this from your trig. Sine starts at 0 and goes up and down and up and down. Probably not too pretty, but something like that. Cosine starts at 1 and goes down. I can't get these to line up. Okay. Let me try this again. Okay. I'm going to put my points in and then try to get the curve to fit. 1 here, 0 there, minus 1 here, 0 there. See, I know what the answer is, so I know where to put it. 1 there, 0 there, minus 1 here, 0 here, and so on. So this is how the cosine goes. And that is how the cosine looks. Okay? And just what I was doing is a hint on what. What does the derivative tell you? Slope of the tangent line. And right here, the sine here, what does it look like? That slope is awfully close to.
1.
1. And sure enough, cosine is 1. And what does it look like the slope is close to here? 0. And cosine is 0. Okay? What does it look like the slope is here? -1. And that's what cosine is. -1 down here. Okay? And what does it look like the slope is here? 0, you get back to 0. Here, 1, there you are at 1. Here, 0, there you are. Here, -1, there you are. Here, oops, here, 0, there you are. And then you keep on going, okay? So, derivative of sine is cosine, or at least this sort of makes you feel warm and fuzzy about it being that way, right? But let's think about cosine. What's the derivative of cosine here? It comes in like this. Cosine's even function. So what's the derivative here? 0, there's sine. But what's the derivative here? -1, but this is +1. So that's how you have to have a minus there. Derivative here is 0 again. Well, -0 is still 0, so that's wet. But here, the derivative is 1, but you have to take the negative of it to make it negative. So you see, that's where the minus comes in for the derivative of cosine, because it's going a different direction. Sine, derivative of sine is cosine, derivative of cosine is negative sine. You have to put the minus sign in. I don't know if that was helpful, but at least it's easier than doing a limit. I mean, it's not as precise. I admit that. Okay. Now I guess we're ready for some functions. Okay, if there's your function, 2 sine theta, 2 sine x, I like to say theta. Never mind. What is y prime? 2 times cosine x, because derivative of sine is cosine. All right. This is too easy, isn't it? Shucks. All right, who came up with this? All right. What is that? I don't know why they rewrite it, but what did they do? How would you rewrite that? 1/2 of sine x, okay? That was really helpful, okay? See, we don't mind numbers in the denominators, only variables or functions in the denominator. So what will y prime be then? 1/2 cosine x. I wish I could make it harder. You can't, I can't, yeah. Or you could write that as cosine x over 2 since you started out with sine x over 2. So either way you do it, both of those are correct answers. Okay? I won't fall down. Okay. How about this one? Oh! Can you do that? Sure you can. What's the derivative of that? 1 minus sine x. Perfect. Derivative of x is still 1, and derivative of cosine, remember, was minus sine. Got it? Okay, good deal. You did the graph in your head? No, you didn't. Okay. All right, how about this one? Y is cosine x minus pi third sine x. What's your y prime? Negative sine x is the first part. Minus what? Minus pi over 3 times cosine x. Yeah, this is just a constant, a coefficient. Just pull it out. Take derivative of the sine as cosine. The minus stays minus because derivative is that. This one went to plus because derivative of cosine is sine. Is negative sine. Make sense? All right, good deal. Do they have an E? I don't think so. No, they don't. All right. So that was example 8. Any questions on that? Now they have a little technology blurb at the bottom of page 115 saying a graphing utility can provide insight into the interpretation of the derivative. So use it if you want to. I guess it does. Okay. So now we look at rates of change, which is what we did, why Newton wanted to find derivatives in the first place. Okay. Instantaneous rates of change. We have seen how the derivative is used to determine a slope. The derivative can also be used to determine the rate of change of one variable with respect to another. The rate of change of one variable with respect to another. Okay? Hang on to that thought. Applications involving rates of change occur in a wide variety of fields. I bet you all dealt with rates of change coming in this morning, didn't you? Did any of you? Okay, yeah. Sometimes it was going along pretty nicely, and sometimes it was not. Okay? Yeah, I ran into several problems like that coming in. And when I looked down at that little gauge in front of me, what was I looking at? Say again? Which is a rate of change. The change of your distance with respect to time. Time rate of change. And when I stomped on that little pedal down here, what was that called? Accelerator. And what's an acceleration? The change of your speed with respect to time, that's accelerating. Changing your speed. So yeah, you're doing it all the time. And when I really stopped on this, what was I doing to my poor old gas tank? I was decreasing my miles per gallon. There's another rate of change, okay? So when you go to cruise control, maybe that would have improved that a little bit. Okay. So you're dealing miles per gallon, gallons, you know, lots of things are rates of change. That was just driving in this morning, okay? A few examples of are population growth rates, okay, which in the U.S. is going downhill, at least native population, okay? We won't get into the politics, okay? I'll try not anyway. Production rates, yeah, we're interested. How are we producing? Guess what? Our administration is interested. They're having them send out every week a comparison to last spring to see if we have as many students enrolled, you know. Somehow that's our problem, I guess. But anyway, water flow rates, or say the air coming out of the vent here. We're supposed to have so many air changes per hour with so many people in a room. You know, those are all flow rates. Water flow rate, velocity, we just talked, and acceleration. All over the place, rates of change. Okay? Either of you pitchers, I don't think so, are you? Oh, you are. You're interested in rate of change every now and then, aren't you? Yeah. Fastball as opposed to a slider or a curve or something else. You're a change up, rate of change, right? Okay, never mind. All right. A common use for rates of change is to describe motion of an object moving in a straight line. Okay? Such problem, now this is a pretty simple problem. it's customary to use either a horizontal or vertical line with a designated origin to represent the line of motion. That's a poor sentence. Designated origin to represent the line of motion. How does the origin represent the line of motion? I don't know. On such lines, movement to the right or upward is usually considered to be positive. Movement to the left or downward is considered negative. Okay. The function S that gives, that's not functions, that's the function space S, that gives the position relative to the origin of an object as a function of time is called the position function. S of t is usually what they use for a position function. If over a period of time, delta t, a little change of time, the object changes its motion by amount delta s, then delta s would be your s of t plus delta t, where it was a little bit past t, minus your s of t, where it was before you started the motion, right? So that's your delta s. Then by the familiar formula that rate is equal to distance over time, we have the average velocity is the change of distance, there it is, over the change of time, there it is. Change of s over change of t. Your average velocity formula. Okay. Here's example 9. They move right into an example, huh? Billiard ball is dropped from a height of 100 feet. Okay, that's where you're starting. Way up there, 100 feet. The ball's height at time t is the position function of s is minus 16 t squared plus 100. Where in the world did that come from? You don't need to know that for the course, but anyone know? Where is minus 16 come from? Yes, the acceleration due to gravity in U.S. customary units, feet per second squared, is 32 feet per second squared, and your formula here is 1/2 at squared. Okay, so 1/2 negative, and it's going downward, so it's negative. Gravity pulls down. Every place on this earth. Okay, so it's negative 16 t squared. Now, why there's no t term here? The t term would be whatever your initial velocity is. But the ball was not thrown down, it was dropped. So your initial velocity is 0. So that's why you have no t term in there. And what was your initial position? 100 feet. So that's where that came from. You don't need to know it. I just went over it. S is measured in feet. T is measured in seconds. Remember, feet per second squared. That's where that came from. Find the average velocity over each time interval. First from 1 to 2, next from 1 to 1.5, and last from 1 to 1.1. So we're looking for average rate of change between those two. How are we doing? We ain't going to get this one done, are we? This would be where we'll start next time, okay? But we don't have to start with the explanation, because y'all are all going to remember that, aren't you, over the weekend? Sure you will. Okay. Homework exercises here. Yes, okay. I know you can do number 5. It's both at Calc Chat and at Calc View. You can do any of the odds 7 through 25, a whole passel of them there. They're all at Calc Chat, 17's at Calc View. You can do either 27 or 29 or both. They're both at Calc Chat, 27's at Calc View. You can do any of the odds 31 to 37. They're all at Calc Chat, 37's at Calc View. You can do any of the odds 39 to 53. They're all at Calc Chat, 43's at Calc View. You can do either 55 or 57. They're both at Calc Chat, 55's at Calc View. You can do any of the odds. Interesting, they got you doing that. Yeah. Any of the odds 59 to 63. They're all at Calc Chat, 59's at Calc View. Do either 65 or 67. They're both at Calc Chat, 67's at Calc View. You can look into doing 69 or 71. That's up to you. They should be pretty easy. 73, they should all be at Calc Chat. 75 is sketching a graph. I'll let you do that if you are interested. you can do either 77 or 79. They should be at Calc Chat. You could do 81. That should be at Calc Chat. And I think the rest of these we might want to hang on to until we finish the last part of that section. Good deal. Can y'all hang off of those for that long? Okay. Y'all are fine. Okay. We'll pick up and go from there. Have a great weekend. Of course, to make it good, work on calculus, okay? The test and homework. It'll make it really good. What's that? I'm sorry?
I don't test what's due today.
Oh, no, it's not due today, but you can turn it in if you're through with it.
When is it due?
When you finish it. Yeah. I gave you a week to do it. Did I give it to you a week ago?
Yes, sir.
Oh, okay. So if you want to turn it in, you can. But if
It's not
you...
work, it's not saved.
It's not.
My name's on work.
Okay. Thank you. Appreciate it. Okay. If you got it through, I'll take it. If you still want to work on it more, you can.
Oh, okay.
Okay. You're okay with that? Okay.
Okay, I have a question.
Okay.
So basically, in vertical asymptote, it's like as far as like number 9, like what's the definition of vertical asymptote? Like it's not what it's undefined, right?
Not necessarily. Vertical asymptotes are always where it's undefined, but not all places where it's undefined will be a vertical asymptote. Now you did it right here, because if you can eliminate that one, sure, it's undefined there, but it's going to be a hole in the graph at x equals 7.
Right.
But x equals -3, no way you're going to have a hole in the graph there.
Right.
That's going to be your vertical asymptote.
Okay.
If you can't eliminate it, then yeah.
Okay.
Does that
How
answer?
do you know that the other one, where it's like the undefined with the hole in the graph?
Well, if you could eliminate it, it was undefined in the original problem, but you've eliminated it, so you just have a hole in the graph there.
Which is not an asymptote.
It's not an asymptote. Asymptote is where it goes to infinity on either side. See, the hole in the graph, it goes right towards that,
Right.
because it misses it.
Gotcha.
Thank you.
I have a general question.
Okay.
If the limits approaching one number is different from the left
And from the
and
right,
the right, that means there's
the
no
limit
limit.
does not exist at that point.
Does not exist.
You could have one-sided limits at both sides, but if they're not the same, the limit at that point doesn't exist.
Correct. Okay.
Good deal. Who was it I asked to see? I bet it was Elise. Was it? Yes, it was. She already gone? Oh. Just want to say
I
something.
just want to ask you a question.
Sure.
After you're done, I want to